Hello, welcome. Let's try to solve another Leetcode problem 1145 binary tree coloring game. So I'm not gonna read the descriptions one by one, but definitely I'm gonna explain it. I know some of us may not understand what is the description because sometimes it is a little bit confusing by just reading the descriptions. But I think it is okay. You just need to understand the basic idea. Maybe you still don't understand it. You're gonna maybe check the tutorials or descriptions from others. Maybe they're gonna explain what is the meaning of the problem. So actually for the description, it is just some idea like that. Let me just make a drawing. So according to the description, we are having a node from 1 to n. So the node inside of the binary tree gonna be have a value from 1 to n, and the first player gonna have a value which is node x. So let me just make a drawing. So in this drawing, so this node 3, x equal to 3, and this is the node 3, and all the nodes are unique. So this is the node which first player choose, which the first player chosen. So maybe it is a color red. So that is just an example. So let me make a drawing. Maybe make it make a better drawing and use the color red. So currently for this node, it is node 3. This is chosen by the first player, but I am the second player. So this means I can choose other node except this node 3. But I need to decide which node I need to choose. Let me continue to use the white color. So for this one, I'm gonna use a parent. So for most of the cases, if I have a node 3 that is chosen by the first player, because I don't know, because I know where the root of the tree, but for explaining the problem, I know there's a node which is 3. It may be here. If it has a left tree, if it has a left child, so this is gonna be the left child. So I'm gonna use a triangle to represent it. Because I don't know how many nodes inside. So this L means this node is its left child, but after this left child, there can be many nodes. So this is for the right child, this node, and after this right child, it can be many nodes. So this is actually gonna be the left subtree, and this gonna be the right subtree. And for this one, this node gonna be the parent of node 3, but just after the parent, it can be many nodes. So now we're gonna split this tree according to this node 3. We're gonna split it into 3 parts. So the parent part, the left part, and the right part. So the idea is that for the second player, I want to choose as many nodes as possible. So for example, if the first player, this is definitely chosen by the first player, it is 3. So what is the next node I can choose as I am the second player? So if I were to choose a blue, definitely I can choose some areas, maybe here, or maybe here, or maybe here, but anywhere should be okay. But the greedy idea is that I wanted to choose as many nodes as possible. So I wanted to choose this node. I mean, it should be the left child. Because if I choose the left child for the next turn, if the first player wanted to choose a red one, so which red one gonna be okay? So the first player cannot choose these areas. Because the first player must choose a node which is connected to this node 3. It can be the right child, or it can be the parent, but it cannot be the left child because it is chosen by the second player. This is the description of the problem. So this means for the first player cannot choose here because it's not connected. So the first player must choose a node maybe here, or maybe here. But for the second player, it must choose a node in these areas. So this is the meaning of the problem. Let me just use the color red. So this means if the first player chooses a red, so the second player chooses a blue, it must be as close to the first player as possible, because in this way the second player gonna choose a maximum of these areas, and the first player gonna choose a maximum of other areas. Maybe this is 3 connected to the parent and connected to the right child. Maybe just those areas that are gonna be the first player, and these areas can be only be the second player. So this is the greedy idea. Let me just go back. So this means for the second player, if the second player wanted to choose a node, it must be connected to this node 3, because only in this way this is gonna be the greedy idea, and in this way the second player gonna choose the node as many as possible. So the second player can still can choose this node or this node or this node. It means for the second player it can choose the left child, right child, or the parent. So if the second player chooses this left child, so that means all other areas are going to be the first player. Because it is connected directly, and if the first player were to choose a node, it must be connected to the first player. If the second player were to choose a node, it must be connected to the second player. So this means if we already know the left part size, I'm going to use ls, and we also know the right size. Maybe I'm going to use a white color. So if I know the left size and the right size, and I also know the parent size, PS, I'm going to use the parent size. So definitely I need to calculate the maximum of the 3. So the maximum of the 3 going to be the maximum node the second player can choose. And then what left behind is n minus the maximum. So that's going to be the first player. So if this second player maximum is more than n minus maximum, so that means I can win. The second player can win. Actually, it means 2 times maximum should be more than n. We just need to 2 times. So this is going to be a times, and this is a maximum. Should be more than. If I can get such kind of formulas, I'm going to return true, otherwise I'm going to return false. So now the problem is that how can we calculate the left size or the right size or the parent size? Actually, we don't need to calculate the parent size. So if we know the left size and the right size, so the parent size is going to be n minus left size minus the right size and minus this node 3. N minus 1 minus the left size minus the right size. So this is going to be the parent size. And I just need to compare the 3. Left size, right size, and the parent size. And 2 times the maximum. So this is 2 times the maximum, should be more than n. So this is going to be the final formula. And now the problem is that how can we calculate the left size or the right size? So for calculating the left size, we can use a post-order traversal of binary tree, and also for the right size, we can use a post-order traversal. Because for post-order traversal, we're going to always finish the left part and the right part before we get to the parent. So this means if we use a post-order traversal, definitely we know the left size, and then we know the right size. And if we want to know the size of node 3, definitely left plus right plus 1, it's going to be the size of this node. And similarly for all other subnodes, it's the same idea. If we want to know the size of the left part, we're going to use the post-order traversal. We're going to calculate the child first, left child, right child, and then plus 1. It's going to be the size of the left tree, and then the size of the right tree. And then we're going to know the size of this node 3. If we know the left size and right size, definitely we solve the problem. Now let's just use this kind of idea to solve the problem. So I'm going to use a DFS. I'm going to prepare a node. So if not node, so if this is a leaf node, so I'm going to return 0. Because my calculation is I'm going to use the post-order traversal to calculate the size. So the left size and the right size are going to be on DFS. I'm going to check its child, not dot left, and DFS, not dot right. And finally, I'm going to return left size plus the right size plus 1. So this is going to be the return. but inside I need to record the left size and the right size. Yeah, but how can I record that? So the condition is that if the not dot value equal to x, this means I find the node x. So for this example, the x equal to 3. If I find this node, so I'm gonna start record the left. So I'm gonna start to record the left size, right size, and the parent size. So the left size is 1, right size is 1, and the parent size is 1, 2, 3, 4, 5, 6, 7, 8. It's gonna be 8. Yeah. So if I already know 811, so what is the maximum of this 811? It's gonna be 8. Yeah. So if this maximum 8 times 2 more than n is 11. Yeah, so 16 is more than 11, definitely it is true. So this is the idea. Now, so if I find the value which is equal to the x, if the value of the node equal to the x, definitely I can record the left size. So I'm gonna use a global variable self.left size and self.right size. So it's gonna be the left size and right size. Yeah. So there's only one condition it is equal to x, because this is a post-order traversal. If I traverse this node, definitely I'm gonna record the left size and the right size. Yeah. Now let me define the global variable left size and self.right size. It's gonna be 0 and 0. I'm gonna run the DFS. I'm gonna start from the root node, and finally I'm gonna return the maximum of some value times. I'm gonna return the formula. It should be more than n. Yeah. So inside it's gonna be the self.left size, self.right size, and n minus self.left size minus self.right size minus 1. Yeah, so this is what I explained before, this kind of formula, 2 times left size, right size, n minus 1 minus left size minus right size should be more than n. Yeah, now I think that's for it. Let me just run it to check if it works. As you can see, it works. Now let me submit it. Yeah, as you can see, it's pretty fast, and it passed all testing cases, and the time complexity is O(n), and the space complexity is also O(n). Because for the maximum time, actually, I have to traverse all the nodes before I know the size, and this is just a post-order traversal. For a post-order traversal binary tree, so the time complexity is going to be O(n). As this is a recursive function, so if the tree node is just linear, so the space complexity is going to be O(n). Otherwise, the space complexity is going to be log n. Yeah, so this is why the space complexity is also O(n). And the number of nodes is just 100. That is why it's so fast. I think that's for it. Thank you for watching. See you next time.